So tonight we're going to be looking at the first part of 2 nights on how to solve some really rigorous, really difficult kinematics problems. So kinematics is what we've been working on so far and kind of building up to. And the word kinematics means motion with constant acceleration. So we're going to look at how to solve some really complicated problems tonight. Along with doing that, I want to point out some things about your textbook, so you're going to get a good textbook overview. This textbook can be really helpful. It has a lot of nice study features for when you're studying for quizzes and exams, and I'm going to help you go through some of those tonight as well. If you will turn to page 45 in the book, maybe pause the video if you need to, you'll see, starting on page 45, kind of a big picture box, and that tells you a really brief summary of this chapter. So if you look at where it says looking back, that's 2 paragraphs to summarize the whole chapter we just did. And then looking ahead tells you how the chapter we just did relates to the chapter we're about to do. So kind of what you now know, what you're about to know. And then chapter summary under that hits all the key points for each section. And tonight we're going to be looking at the key points for section 2.5 on page 46. So key points for section 2.5 on page 46. You will also notice, once you're on page 46, over on page 47, there's some problem-solving summaries. And then there's 3 categories. Each one's a type of problem you might be asked to solve from this chapter. And then it tells you how to solve them and shows you some examples. So if you're having a lot of trouble with one type of problem, you could come to the problem-solving summary at the end of whatever chapter we're on, find out what type of calculation it is, read the relevant concepts, so what you absolutely have to know in order to solve that problem, and go over to related examples and look at a few examples of those problems being solved for you. So, all kinds of examples in your textbook, all kinds of instructions on how to solve problems, and every chapter has a little box like that, the problem-solving summary, that shows you where to find out how to solve any type of problem. And then conceptual questions. So if you're ever like, I'm not really sure that I've got this, there's some basics I don't know. You can go through the conceptual questions to see if you really have down the basics, and the odd-numbered conceptual questions have answers in the back of the book. So you could even check your answers like that. Alright, we're going to be focused on that 2.5 section summary over on page 46, the very bottom of page 46, where it says motion with constant acceleration. Before we get into problem solving, in this video, you really need to know what acceleration is. There's a whole really great section in your textbook on page 26, if you see where it says 2.4 acceleration. You were supposed to read this before the video. I'm going to go over a couple quick parts with you. Let's look at that first paragraph. Just as velocity is the rate of change of displacement with time, acceleration is the rate of change of velocity with time. So acceleration is how much velocity changes in a certain time. Just like when we took our position time graphs and we found the slope of them to get a velocity time graph. Bottom one's 0, by the way. Acceleration is also the change in velocity. So an acceleration graph would be the slope of a velocity graph. So if this is a velocity time graph, the acceleration time graph would be like this. Okay, so acceleration is slope of velocity. Formally, or with words, acceleration is how much velocity changes in a certain amount of time. So just like your velocity is how much your position changes in a certain amount of time, your acceleration is how much your velocity changes in a certain amount of time. If you are having trouble with that definition at all, look over that chapter until you get it. Call me, call a friend. Make sure you understand, not chapter, that section. Make sure you understand pages 26 and 27, starting at acceleration and ending at graphical interpretation of acceleration. It's just a really great explanation, I think, in the textbook, and if you have trouble understanding it, please call somebody. You cannot survive the rest of this video without knowing what acceleration is. Alright, that's it. Here we go. I'm going to show you 3 example problems, each of which is pretty long, so divide up your page wisely. My goal tonight is just to show you how to solve a few complicated problems using motion with constant acceleration. So you'll notice in that section summary, there are 5 equations, each with a title. We're going to look at how to use some of those equations tonight. You're going to look at how to use more of them tomorrow, and both days in class you'll be using those equations. So let's get started. The point of this is really just to understand using these equations. First example, a light plane, and by the way, in physics, whenever you see the word light, this means ignore the mass. And since we haven't talked about mass yet in any kind of relevant way, we don't really need to know we ignore the mass, but just to go ahead and give you that, the word light in a physics problem usually means ignore the mass. A light plane must reach a speed of 33 meters per second for takeoff. How long a runway is needed if the constant acceleration is 3 meters per second, or 3 meters per second squared? All right, first problem-solving strategy is to write down what you know. So, first, I'm going to write down what I know. I know that the final speed of that plane is going to be 33 meters per second. So I'm going to say final velocity, 33 meters per second. And then I'm going to say that the acceleration is 3 meters per second squared. And I'm looking for the distance traveled, or x, is what I'm looking for. So now I want to find an equation that takes final velocity, acceleration, and gives me distance. Alright, looking at the equations, I actually see 2 that would be useful. First, position as a function of time and velocity, equation 210, gives me position if I tell it where I started, x naught, and initial velocity, which here we get to assume the plane started with 0 velocity, because it says we're reaching 33 meters per second, and final velocity, 33 meters per second. Oh, and a time. We don't have a time, so maybe equation 210 might not be useful, so let's move to the next one. The other one I saw that could be useful is equation 212, velocity as a function of position. Final velocity, v squared, is v naught squared. We said our initial is 0. Plus 2a, we have a, acceleration, times final x, that's what we're looking for, minus initial x, x naught. We can assume, let's just say that our plane starts at position 0. So let's set our plane at the origin, and I'll go ahead and make that note. So I'm going to assume that the plane's initial position is 0, so it starts at the origin. And I think we found our equation. There's also a simplified version of this equation. So it says what I just read equals v naught squared plus 2a delta x, change in x. So let's go with that. And I'll even use the simplified version. We're using the equation v squared equals v naught squared plus 2 times the acceleration times the change in x. Okay, so we know our final velocity needs to be 33 meters per second. Our plane has to take off from a runway, and if you've ever been on a plane, everybody has to get on the plane, so it can't be moving at that point. So I'm going to go ahead and say that our initial velocity is 0. 0 squared is still 0. All right, plus 2 times the acceleration, 3 meters per second squared, times our change in x. And since we set our initial x at 0, our change in x will also be our answer. So however the plane has to go from 0 is how long our runway will be. Okay, I've cleaned up the slide a little bit. And now we're ready to keep going. At this point, I can ignore the 0, not going to matter. And we're trying to find delta x, so I'm going to go ahead and divide both sides of the equation by everything except delta x. Alright, so now I have 33 meters per second squared. All squared. Oh wait, nope, that 33 meters is not second squared, it's just 33 meters per second, my bad. So 33 meters per second, all squared, divided by 2 times 3 meters per second squared, equals delta x. Alright, and now I'm going to go ahead and calculate that out. So we have 33, sorry I dropped my calculator, 33 squared divided by 2 times 3, so, and when I do that math, I get that the runway had to be 181.5 meters long. Alright, if you need to look back over that, anything was confusing, feel free to rewind. I'm moving on to the next example. Alright, that last example, I started out by plugging in numbers. I did that just to give you a chance to get used to these equations. But from now forward, I will manipulate the variables first and then plug in the numbers, which is what you should always do. So that first one was simple, didn't require a lot of manipulation, and didn't want to scare anybody too fast. But now we're going to just variables, plugging in numbers at the end. If you're not sure what I mean by that, you'll see in just a second. Here's our problem. A car slows down from 23 meters per second to rest in a distance of 85 meters. What was its acceleration? And did you assume the acceleration is constant? Alright, this looks like another good one for the same equation we used last time. V squared, so final velocity squared, equals initial velocity squared, plus 2 times the acceleration times delta x. Alright, I am not going to sub in numbers this time. First I'm going to solve the equation. We are looking for acceleration. And I see that we got that equation out of the section called motion with constant acceleration. And so we are assuming that the acceleration was constant. So yes, I did assume that. Alright, now let's solve the equation just using the variables. We are trying to find acceleration. We got to get it by itself. So first, what I will do is move velocity naught, or initial velocity squared, over to the other side of the equation by subtracting. So I have v squared minus v naught squared equals 2a delta x. So now I'll just divide by everything that's not a. 2 delta x. Whoops. 2 delta x. Okay, so that leaves me with, just going to rearrange things a bit, delta x equals v squared minus v naught squared. Oops. Okay, so mistake I made. Delta x is not the thing left over here. It is a. So a equals v squared minus v naught squared all over 2 delta x. Alright, just like last time, I have cleaned up the equation. Now that we've got everything arranged how we want it, so a equals, and then all the stuff we've got to plug in to find a, now we'll plug in the numbers. So, we slow down from 23 meters per second to rest, so our final velocity, rest, is 0, and 0 squared is just going to be 0. Our initial velocity, v naught, is 23 meters per second. Square that. And we have 2 times our distance of 85 meters. Alright, now I'm going to do the math out. I can ignore the 0 squared since that's just 0. And I have 23 squared, which gives me, moving down and over. Notice this negative here in the equation. That doesn't go away. that negative stays. So 23 squared was 529, and then keeping my units, that would be meters squared over seconds squared. All right, divided by 2 times 85. 2 times 85 is 170 meters. So now I do 529 meters squared per second squared divided by 170 meters. Notice that 1 meter will cancel with one of the meters in the meters squared, leaving me with, oh, you know what I did? I talked about keeping that negative, and then I didn't keep it in. So that's negative 529 meters squared per second squared on top. So when I do the division, I get negative 3 point, and I'm going to round to just 3 digits, so 3.11 meters per second squared. All right, if you need to look over that one again, feel free to do so. All right, a sprinter bursts out of the blocks to top speed of 11.5 meters per second in the first 15 meters of a race. What is her average acceleration, and how long did it take her to reach this speed? All right, this time we're actually going to use 2 of the equations, because first it asks what is her average acceleration, then it asks how long did it take her to reach this speed. So let me point out to you the 2 equations I think we should use and how we'll get there. So we're going to use our old friend, velocity as a function of position. V squared equals V naught squared plus 2a delta x. Because we have a initial velocity of 0, she bursts out of the block, so a racer starts from 0, final velocity of 11.5 meters per second, and we have a distance of 15 meters. So let me write that all down. Our initial velocity is 0, our final velocity is 11.5 meters per second, and our delta x is 15 meters. So that's the first equation we'll use. Let's go ahead and do that one. Alright, so I've given myself more room to solve this problem. Alright, in the last example, we solved that equation at the top for acceleration. So if you need to see that process of solving it again, please look back, but I'm just going to go ahead and write down what we got when we solved it. We found that acceleration is final velocity squared minus initial velocity squared divided by 2 times delta x, distance traveled. Alright, now let's substitute everything in, since we've already got our equation in the right form. 11.5 meters per second squared minus 0 squared is 0, we've seen that several times, divided by 2 times how far the plane went, how far the person went, 15 meters. Now we're ready to do that math out. 11.5 squared is 132.25 meters squared per second squared. Notice that the units get treated just like variables, they get squared too. 2 times 15 is 30 meters. Do that division, 2.25 divided by 30. Notice that one of the meters will cancel with one of the meters, and we're left with 4.4, I'm going to round 1 meters per second squared. Alright, that's the first part of the problem. Next up, it asks, how long did it take to reach this speed? If you need to pause and do anything with this part of the problem, please do so now, and then I'm going to move on. Okay, in the last problem we found acceleration is 4.41 meters per second squared. Now we're looking for time. In the problem it says, how long did it take her to reach this speed, and that speed being 11.5 meters per second. So let's review what we know. We know the acceleration we found on the last slide. We know her initial velocity is 0. We know the final velocity is 11.5 meters per second. We know she went 15 meters when reaching that velocity. Now we're going to try to pick out an equation that takes the information I just wrote down and gives you time. I see the equation on page 46 in section 2.5. Why don't you take a minute, see if you can find which equation we should use here. Pause the video if you need to. Alright, I'm going to go with equation 2.7 because it has in it final velocity, which we know, initial velocity, which we know, acceleration, which we know, and the only thing left is the time, which we're looking for. So the key thing I've been doing when finding these equations is picking one that has everything we know, and then the only thing left, what we don't know. So if the equation had like 3 things we don't know, it wouldn't work. It can only have one thing we don't know. And the one thing we don't know in this equation right now is time. We know the rest. Okay, now we're going to solve the equation for time. First thing I'm going to do is move the v0 over by subtracting. So now I'll have final velocity minus initial velocity equals acceleration times time. And then since I'm trying to get time by itself, I'll divide both sides by acceleration. Alright, so now I have final velocity minus initial velocity divided by acceleration equals time. And I can substitute in now. Final velocity is 11.5 meters per second. Initial velocity is 0. Acceleration is 4.41 meters per second, which we found in the last problem. Alright, I can ignore that 0, and now I'm just dividing 11.5 by 4.41. 11.5 divided by 4.41, and I get rounding 2.61 seconds. What you might want to take a little bit to do is try that dimensionally. Make sure it does work out to seconds. So see if my answer is dimensionally correct, like you did the first day we did a problem set. Alright, once you've got this, rewind if you need to, whatever, go to the next slide. I'm going to do a quick wrap up, make sure we got it all tied together. So you might be asking yourself, why did Mr. Melvin just go over examples of problems tonight? Well, in past days in class and past nights, you've gone over what position means. We've talked about exactly what it means, so you know what position is. We've gone over what velocity means. At the beginning of this slideshow, we went over what acceleration means. You know what they all mean. You know that velocity is change in position over time, acceleration is change in velocity over time. Now that you know that, you're just ready to solve problems. So that's why I didn't do a lot of conceptual work tonight. You were ready for problem solving. Make sure you've done the before and after reading questions. If you have any questions, call, text me or a friend, and I will see you tomorrow.